You are welcome to the GMAETS 41's live stream class. Today we are going to give attention to another part of physics. And like I have already broadcasted on this channel, we are going to give attention to measurement of heat energy. Measurement of heat energy. In this concept of measurement of heat energy, we are going to give attention to the concept of specific heat capacity. Specific heat capacity, we'll talk about the thermal or heat capacity. We'll talk about the concept of quantity of heat transferred in the case of heat lost and heat gained. And we shall also give attention to the concept of latent heat. We'll deal with latent heat. We'll deal with specific latent heat. We'll talk about the latent heat of fusion. And of course, we're also going to give attention to latent heat of vaporization. So once again, I welcome you to this class. Grace, you're welcome to the class. So I hope you can hear me very well, right? Remember, as usual, all right, it's our culture because we want as many people as possible to follow along and learn from the comfort of their home. The concept of math, science, and engineering from the GMAETS 41's platform. Therefore, help me to share this link to your friends. Those whom you know are sitting for GMAETS, those in SS1, SS2, right? Those in advanced level as well too can benefit from this class because they might be dealing with a course that focuses on measurement of heat energy. Good evening, every one of you. You're welcome. Elijah, Queen Omar, you're welcome. All right. Ebere, thank you for letting me know that you can hear loud and clear. And without wasting time, let's get to the business of our class today. Now you have this measurement of heat energy. When we talk about the concept of measurement of heat energy, it is important for you to know what heat as a form of energy actually is in the first place. So we're going to give you a quick summary, and as usual, we will move on straight to the questions that have been provided by the GMAETS 41's physical JAM lesson student, JAM and WAEC students. We have these questions that have been provided by, I think, group 2, right, of the GMAETS 41's JAM lesson. So we're going to focus on this question. There are about 10 of them. All right. And in our physical class, we've actually treated the concept of measurement of heat energy. So we're going to move on straight to that. I want to believe that all the friends that are joining, connecting from any part of the world, right, in one way or the other, you must also have learned the concept of heat energy. I've given you the background of what we are going to cover, and I'm going to give a quick summary to read so that we move on to the questions we have here. No time. First of all, when we talk about heat, we want to remember this fact that heat energy is energy in transition. What do we mean by energy in transition? That is energy that moves across the boundary of a system. Let us assume that I have this as a system, and then this is the system, like I said, system, and then outside we have surrounding. Now, energy is a form of heat energy, rather is a form of energy that can move in and out of this system. So we say that heat is a form of energy that is in transition. It moves. That is why in defining heat energy, we define it as that form of energy that flows from region of high temperature to a region of what? Low temperature. Once again, heat is a form of energy which flows from region of high temperature to a region of lower temperature. So if I have this point as a point, a region where temperature is high, and I have this point as a point, a region where temperature is low, heat energy is going to flow from this region of higher temperature to the region of what? Lower temperature. Therefore, we expect something, if heat moves from where it is, you have a higher temperature to where you have a lower temperature, it will be concluded that this point of higher temperature, heat is being lost there. And where it is flowing to, the point of lower temperature, the region of lower temperature, we can say that heat is being gained at that point. In talking about measurement of heat energy, there is this particular quantity of interest where we talk about the concept of specific heat capacity. Specific heat capacity. So without wasting time, we are going to define the specific heat capacity. But before then, permit me to write on the board the formula for calculating quantity of heat, or simply heat energy. Remember, heat energy depends on temperature. It is a function of temperature, since temperature controls heat energy. So we can say that heat, I'm going to use H for it, quantity of heat is equal to the mass times a quantity, small letter c, times delta theta, which is change in temperature. That is the formula for calculating quantity of heat. Simply mc delta t. That m is the mass of the substance that is receiving the heat, or that is losing the heat. The C there is known as specific heat capacity, which is a very wonderful, one key quantity we are going to define. As a matter of fact, once you are able to measure that quantity, you can calculate the heat energy of any substance. Then delta T, just like you learned from our previous class, I guess yesterday, is simply change in temperature. Now that you've known the formula for calculating quantity of heat energy, I'd like us to look at making that C, specific heat capacity, subject of the formula. If I make specific heat capacity C subject to the formula, I am going to get H divided by M delta theta. If I call this equation 1, I'll call this equation 1A, because I got that equation 1 from 1A. Remember, I'm just giving a summary of this. So once we start solving questions, we start answering questions provided. If anyone leads us to calculations, when I start solving, there will be no time to waste. This is going to be a short class as compared to classes we've had before. Now, this C is called specific heat capacity, like I said. C is equal to specific heat capacity. And the unit, in the unit of joule per kilogram Kelvin. You can write it this way, or you can write it as joule. That per kilogram can be written like this, and then per Kelvin, because it is energy divided by mass times temperature. Energy is in joule all over, which is our per, as seen in this unit. Mass is kilogram, and then the temperature is in Kelvin. Let us now define the specific heat capacity of a substance, C. We're going to use equation 1A here to understand the definition. If you look at this, this is simply energy divided by mass and temperature. So we define specific heat capacity as the quantity of heat required, to raise the temperature of 1 kilogram of that substance, to raise the temperature of 1 kilogram of that substance through 1 Kelvin. Through 1 Kelvin. That is through 1 degree rise in temperature. Once again, remember what we are defining is not just heat capacity, because we are going to talk about heat capacity soon. We are defining specific heat capacity. Specific. So we are a kind of particular. We are certain. We are measuring a particular quantity, right? A particular mass of a substance. Or per se, we are trying to find out the energy required for a specific mass of that substance. And that specific mass is 1 kilogram. So going by definition of specific heat capacity, it is defined as the quantity of heat required to raise 1 kilogram of a substance. Please take note of that. 1 kilogram of a substance through 1 Kelvin. Through 1 Kelvin, that's through 1 degree rise in temperature. That is what equation 1a is defining. Now let us talk about heat capacity quickly. This is specific heat capacity. Let us now talk about heat capacity. Heat capacity. This time around, we use something like capital letter C, and then maybe I can use small letter P for it. This is heat capacity. Heat capacity. It is not exactly the same as specific. However, it is still the same, but not exactly the same. The difference between both is, in the case of this, you are talking about specific. The heat required to raise the temperature of 1 kilogram of a substance through 1 degree rise in temperature. But this one is just heat capacity. Like when I talk about it to students, I say it is an open heat. What do I mean by that? It is not for any specific mass. Are you getting me right? It is not for any specific mass. So in defining heat capacity, we simply say it is the quantity of heat required to raise the temperature of a substance through 1 degree Kelvin. To raise the temperature of a substance through 1 Kelvin. Once again, the quantity of heat required to raise the temperature of a substance through 1 Kelvin. Or you can say through 1 degree centigrade. Does this make sense? So the difference between this definition and this is that in this case, it is the quantity of heat required to raise the temperature of 1 kilogram of a substance. That's the case of specific heat capacity. But in the case of heat capacity, it is simply the quantity of heat required to raise the temperature of any mass of a substance. And when we talk about any mass, please, it is not 1 kilogram mass. It can be any value of mass of that substance, but not 1. Mathematically, heat capacity is equal to mass times specific heat capacity. So you want to take note of this equation as well too. Heat capacity is equal to mass times specific heat capacity, which implies that if we go back to equation 1, I can actually, in place of this mass times specific heat capacity, I can actually write that quantity of heat is also equal to, remember, heat capacity is MC. So this MC can be replaced with heat capacity, and it will multiply the temperature change, delta theta. So you take note of this. I can call this equation 1b. Reason, I obtained it from 1 using equation 2. So we are done with this concept and their definitions. Remember the difference between specific heat capacity and heat capacity. So that is that. Now quickly, let us now move on to a case of when you are dealing with measurement of heat energy, but then there is no temperature change. In this case of specific heat capacity, in this case of heat capacity, there is a temperature change. So if you're using a thermometer, it can measure the change in temperature. Are you getting me right? But the next aspect you are going to look at is the aspect of quantity of heat delivered to something or removed from something without a change in temperature. Without a change in temperature. Chohan, you are welcome to the class. So we are looking at measurement of heat energy without a change in temperature. In that case, we'll be dealing with change of state. We'll be dealing with what? Change of state. Remember, I'm giving a summary of this so that when we solve questions, you won't have any much challenge. And I cannot remember having released a pre-recorded video on this before. I've not done that. Then this is my first time of taking this class or this topic online. So I decided to make a good, summary as a background to it before we start solving the questions given. At least to be able to benefit other friends that are connecting from any other part, all right, in joining this class. For our students, we've treated this already in our physical class. So let's have something like that, an equivalent of it online. Change of state. When you talk about change of state, usually your examiner will want to test you on perhaps solid changing to liquid and then liquid changing to gas. You know, when solid change to liquid, we refer to that as what? Melting. Melting. We can also use the term fusion. Fusion for it. When solid is changing to liquid. Melting or fusion. If liquid is changing back to solid, it is called freezing. Freezing. Now, if liquid is changing to gas, we call it vaporization. Vaporization or evaporation. Vaporization or evaporation. Now, the difference between vaporization and evaporation is that in the case of vaporization, liquid changes to gas when you heat, when you apply heat. So you have to apply heat in that case, when you heat that substance. For example, if you are boiling water, and then at the boiling point of water, what you see there, you know, molecules of liquid changing to vapor or gas. That process is called vaporization. So vaporization requires heating. It requires heat. But evaporation, where liquid changes to gas, evaporation does not require heating. There is no heat required there. For example, if you open, let's say, your well. What is well here? I don't know. Like here in Nigeria, well is, let me use the word, a pit that is being sunk, dug, to meet the table water, right? Or water table under where we fetch water from. We can pull out water, draw out water from the well. And so in that case, let's assume that in the morning you get to a well, that well was closed overnight, and then you open that well in the morning, you just open, you will see something coming out like steam. That is evaporation process. Liquid molecules are changing to gaseous molecules. Are you following, right? But nobody heated that well. No one heated it. If you go to a river in the morning, because this phenomenon usually happens when you leave that in over time. You know, if you go to a river in the morning and you watch that river, that morning period, any morning period, you would observe, vapor trying to come out. Vapor, that's liquid molecules changing to what? To gaseous molecule. No one heated the river, no one heated it, okay? And so if liquid molecules can change to vapor, we refer to that as evaporation. The process whereby liquid molecules change to steam, to vapor, to gas without heating. But vaporization is a process where liquid molecules change to vapor as a result of heating. In this case of change of state, whenever there is a change of state, the heat we use there is called latent heat. So let us talk about latent heat. Let us talk about latent heat. Latent what? Heat. Latent heat. Latent heat. We're going to use L for it. Okay, it doesn't matter. Let me just leave it this way. Latent heat. The word latent means hidden. So if you hear latent heat, it means hidden heat. So this is the heat required. The heat required to change the state of a substance. The heat required to change the state of a substance without a change in temperature. So if solid is changing to liquid, it will change and there will be no temperature change. The solid will change to liquid, but temperature will not change. If liquid is changing to gas, the liquid will change to gas, but there will be no temperature change. That is what we mean by change of state. The states here are the states of matter, basically solid, liquid, and what? Gas. So when matter is changing from one state to another without a change in temperature, that heat there is called latent heat. Am I communicating? All right. Let us now talk about latent heat of fusion. Latent heat of what? Fusion. Because this latent heat is broken down into two. We have latent heat of fusion, and we have latent heat of vaporization, These are two forms of latent heat. Fusion, where solid is changing to liquid. Vaporization, where liquid is changing to gas. As a result of heating, you heat there, but there will be no temperature change. So let us define latent heat of fusion. Usually your examiner defines it with respect to ice. where ice as solid changes to liquid. Latent heat of fusion is defined as that quantity of heat required to change a solid to liquid without a change in temperature. Once again, latent heat of fusion is defined as the quantity of heat required to change a solid substance to what? Liquid. To change a solid or to change a substance from its solid state to its liquid state without a change in temperature. So you see, if you are defining latent heat of fusion, you specify changing of solid to what? Liquid. Let's talk about latent heat of vaporization. The definition is the same as that of fusion. The only difference is that you are changing liquid to gas in this case, and there will be no change in temperature. So I'll leave you to define latent heat of vaporization. Remember, I told you it is the same as latent heat of what? Fusion, where you change solid to what? Liquid, without a change in what? Temperature. In this case, you are changing liquid to gas without a change in what? Temperature. So I'll leave you to define that. Someone can decide to drop the definition of latent heat of vaporization. Let's see. Joseph, Elijah, Agiebi, Elijah. Very much communication and knowledge is imparted, sir. Thank you very much. I appreciate the commendation. And thank you for always tuning in to GMAETS 41's channel. All right, having talked about latent heat of fusion and latent heat of vaporization, this one links solid changing to liquid. This one links liquid changing to what? Gas. Now we are going to define the specific quantity of this guy. Specific latent heat. Specific latent heat. Once again, we shall define specific latent heat in terms of fusion and in terms of vaporization. Vaporization. Specific latent heat of fusion and specific latent heat of vaporization. Now, remember that here we are no longer talking about just an open latent heat, where no specific mass is required. Just like we talked about specific heat capacity and heat capacity. So that's what we want to look at here. This guy is latent heat. Now we're now looking at specific latent heat, where a specific mass is required. So I'm going to define specific latent heat of fusion and specific latent heat of vaporization. Let's be fast. The definition is similar to these two guys, latent heat. The only thing is you are changing 1 kilogram mass of a substance. You are changing the state of 1 kilogram mass of a substance. That's just the only thing. So we define specific latent heat of fusion. Like I said, your examiner can link it to fusion of ice, assuming that ice is the solid changing to liquid. So we define specific latent heat of fusion or of fusion of ice, if you want to be particular about the substance, as the quantity of heat required to change 1 kilogram of a substance from its solid state to its liquid state without a change in temperature. Remember, I was particular about the mass used. I was specific. The quantity of heat required to change 1 kilogram, to change the state or the solid state of 1 kilogram of a substance to its liquid state without a change in temperature. And that brings us to specific latent heat of vaporization. Vaporization. Specific latent heat of vaporization is defined as the quantity of heat required to change 1 kilogram, to change the state of 1 kilogram of a liquid from that liquid form to its what? Vapor form. Quantity of heat required to change 1 kilogram mass of a liquid to its vapor form without a change in temperature. Having defined this, can we now bring out the formula for calculating the quantity of heat in the case of change of state? Quantity of heat in the case of change of state, H is equal to ml. Is equal to what? ml. I hope this is showing on the board. Oh my gosh, this has cut off. It has cut off. Let me adjust the camera. Let me adjust the camera so that the board will be clear. Good. So quantity of heat required in the case of latent heat is equal to ml. So I can call this equation, let's call this equation 3. Now if you make this L subject of formula, this L is our specific latent heat. L is equal to H divided by N. I got it from equation 3, so I'll call it equation 3a. The unit of L is equal to specific latent heat. Specific latent heat. It can be specific latent heat of fusion of a solid, for example, ice, or specific latent heat of vaporization of a liquid, for example, water vaporizing to its steam form. So, and the unit of specific latent heat, unit is unit of energy divided by unit of mass, which is joule per kilogram. You can still write it as joule kilogram raised per minus 1. So, dear friends, we are done with the background, the summary of this guy. Other things you can work around it when you talk about how to determine specific heat capacity of a substance, or how to determine the latent heat, the specific latent heat of a substance. You know, you hear stuff like electrical method, you hear method of mixture. All those stuffs are stuffs you can just read up, nothing is there. The calculation or answering questions under them is now the next thing of interest. So you can copy out what you have on the board, all right? You can copy out what you have on the board or screenshot, whichever that is faster for you, so that I can wipe the board and we move on straight to the questions that we have to answer in our class today. The questions submitted by GMAETS 41's JAM lesson student. All right. Group 2 of our students have submitted questions on measurement of heat energy. All right. Ebere Ufikaro, you defined latent heat of vaporization is defined as the quantity of heat required to change liquid to gas without change in temperature. That's very correct. Latent heat of vaporization is defined as the quantity of heat required to change liquid to gas without change in temperature. Thank you very much for that definition provided. That is correct. That's the definition of latent heat of vaporization. I'm going to wipe this. Daniel, good evening. You're welcome to the class. It is now time for us to move on to the questions provided, like I said. So let's get to business. I just decided to lay a background work of this guy for the sake of our friends who may have connected to this class, you know, who are not part of our, you know, class, fully kind of our physical class. Because the students who supplied this question are those that attend GMAETS 41's physical JAM tutorial class. So we move on to our very first question, question number 1. Question 1. I will dictate the question as usual. You can follow through. Remember, please, anytime we have live class like this, it is advisable you come with your notes. Let me tell you, the knowledge you are getting from here, at least by God's grace, by the strength, the wisdom that comes from our God and helper Jehovah, the truth of the matter is what you receive from here is so much. Yeah, it's something that can strengthen you beyond your imagination in your various conventional schools. And one thing about GMAETS 41, this platform actually is running a non-conventional school, which is something that actually helps students to learn at their own pace. And let me tell you, whether our generation is accepting it or not, the truth of the matter is the way the world is going now, non-conventional form of learning is at its peak. When I talk about conventional form of learning, that's where you go to schools, you put on school uniform and other things. A standardized non-conventional form of learning, such as the one that GMAETS 41 is running now, is something that can really strengthen your stand in your various schools. So I encourage and implore all of you, when we have our classes, if it is live class as this, get your note ready. You can get a GMAT 41's lesson note. What do I mean? A lesson note specifically for GMAT 41's classes. Like I promised, or like I gave you the good news yesterday, this platform is now set to give the best. We'll be having regular classes, live classes regularly. I'm going to release a timetable on that so that you know how the stuff is going to go. And this is not only going to cover for maybe SS1, 2, 3, WAEC JAM. It's not going to cover only 100 level students, 200 level students. It will go beyond and below. Because I do not take for granted our basic level of learning. Those in primary school from grade 4 to grade 6, from grade 7 to grade 9. That's primary 4 to primary 6, JSS 1 to JSS 3. That basic level of learning is also very, very important. And I am encouraging people to see, families, parents, to see that they make a room to have their children learn at their convenience and at their pace. It's going to help them a lot. All right, please follow up as I dictate our very first question. It reads, 1.95 kilojoule. 1.95 kilojoule of heat is required to raise the temperature of 500 grams. 1.95 kilojoule of heat is required to raise the temperature of 500 grams of lead from 15 degrees centigrade, to its final temperature, Full stop. Taking the specific heat capacity of lead to be 130, joule per kilogram per degree centigrade. Taking the specific heat capacity of lead to be 130 joule per kilogram per degree centigrade. The final temperature is A, 45 degrees centigrade, B, 37.5 degrees centigrade, C, 30 degrees centigrade, D, 22.5 degrees centigrade. So let us solve this question and say, now from the question given to us, the value of heat required was given 1.95. So we know the value of H, 1.95 kilojoule. Convert this into joule by changing this kilo to its metric prefix value. The metric prefix value of kilo is 1000. So this is equal to 1.95 times 10 to the power of 3. 10 to the power of 3 is the same as 1000. So we have that value given. The mass of lead was given to us, 500 grams. Convert it to kilogram by dividing by 1000. That's going to give you 0.5 kilogram. And then we are given the initial temperature of lead. Theta 1 was given to be equal to 15 degrees centigrade. And then we are asked to find its final temperature. Theta 2 we don't know. The specific heat capacity of lead was given to be 130 joule per kilogram and then degree centigrade. So what do we do? Remember, we already know that H is equal to MC delta theta, where that delta theta is theta 2 minus theta 1. So let me indicate it. Final temperature minus initial temperature. So all you have to do is to substitute and calculate theta 2. It's that simple. We know the value of H already, so we can substitute. We have that 1.95 times 10 to the power of 3 is equal to the mass is 0.5 times 130, open bracket, theta 2 we don't know. Theta 1 is 15 degrees. You don't need to convert the temperature here. It's not necessary. You don't need to convert the temperature. Okay? Whether this guy is given in per Kelvin, it doesn't matter. It doesn't matter. By telling you that you don't need to convert the temperature from degree centigrade to Kelvin, it's not because of this unit given, the temperature unit given in the specific heat capacity. That's not the reason. Even if this temperature unit in this specific heat capacity is Kelvin, even if it is Kelvin, there is no need converting. Yeah, there will be no need converting. Because whether you convert or not, you still get the same value. think we met something like that under thermal expansion. Solving for this, we have 1.95. I don't know if I can convert this. Maybe let's convert it to this scientific form it is called, right? Let's convert it to scientific form. If you multiply this by 1,000, it is the same as 195 till you move the point 1, 2, and 3. So 1950. That's equal to 0.5 times 130 is the same as half of 130. Half of 130, that is 130 times 1 over 2, will give you 65. Open bracket, theta 2 minus 15. And this is a waste of time because I could have divided here by 65 directly without wasting my time, so that I make theta 2 minus 15 subject to the formula. That's going to be 1950 divided by 60. We don't have time. I'm going to be a bit faster whenever I solve question, henceforth in terms of calculation. To make theta 2 minus 15 subject to the formula, you divide here by 65, divide here by 65. 1950 divided by 65. Let's see what we are going to get. All right. Assuming there is no calculator, 65 can go into 65 cannot divide 1. All right. So it's 0 remainder 1. Attach the 1 to the 9. You have 19. 65 cannot divide 19. So you still get another 0 remainder 1. Attach 0 remainder 19 because 65 cannot divide 19. It's going to be 0 remainder than 19. Now that 19, attach it to 5. So you get 195. 65 go into 195. Yeah, you can divide. In the GMAETS 41's basic class channel, right? GMAETS 41's basic class channel, I appeal to you, friends, please. Okay, do me good. Type GMAETS 41, GMAETS, maybe after the class, or you can copy it down somewhere. Because I need you, friends, to go and subscribe to that channel. Share it to many people as much as you can also. As you're sharing this channel, share that one also. Reason. It is in that channel I deal with all these basic maths. You see, there's something I said here. Assuming there's no calculator, 65 to divide 1,950. I told you 65, 1 over 65 is not possible. 0, remainder 1. Attach the 1 to this 19. To this 9, you get 19. 19 divided by 65 is not possible. 0 time again, remainder than 19. Attach 19 to 5. Then you have 195 divided by 65. 65 can go into 195. It is in that basic channel I do all this calculation in basic maths. And you guys need this, right? You friends, you need this to help you a lot. So if I have 195 divided by 65, let's see from the knowledge of multiplication how many times this can go. I can quickly decide to reduce by 5 so that the number will be smaller for me. Are you following? 5 into 19 is going to be 3 times, remainder 4. Remainder 4. Are you following, right? Attach the 4 here, you get 45. 5 can divide 45. That is 9 times. 5 into 6 is 1 time, remainder 1. Attach the 1 to 5, you get 15. 5 divide 15, you get 13. So this is 39 divided by 13. And 39 can be divided by 13 exactly to give you 3 times. To give you 3 times. So 65 can divide 195 3 times. No remainder. You are left with this 0. 0 over 65 will give you 0. So this is going to be 30 if you divide 1950 by 65. Therefore, the final temperature theta 2 is equal to 30 plus 15, which is a waste of time because you could have just done that, using the network of your brain directly. 30 plus 15 is going to give you 45. So this is 45 degrees centigrade. And of course, we are done solving this question. We are done solving this question. From the options given, the correct option is option A. Option A is the correct option. So we are done with this particular question. All right, we shall be moving to question number 2. Please, like I said, dear friends, support GMAETS 41. There are several ways you can support this channel. There are so many things you can do to make sure that the pride of quality learning is promoted. I have 2 channels. GMAETS 41 has 2 channels. One is specifically for those from SS1, SS2, SS3, where I can jump students, then advanced level university students. Are you following, right? 100 level, 200 level, 300 level. But should we not neglect our basic level of learning? That is not good. That is not good. I must tell you that from personal experience, what I observe of even people in advanced levels, some of them still have this challenge with basic maths. So without wasting time, you can write down GMAETS, GMAETS 41, basic class. Subscribe to that channel, share the link to your friends, to other ones. The younger ones will also need it. That's the truth, because that's where I break down basic maths. I am not going to be taking my time so much in dealing with this concept here, because all those things waste our time. All right, please, let's help ourselves so that we can also be able to minimize time wastage when we have live classes. All right, thank you very much, Shivan Sharma, for subscribing to that channel. That's appreciated. Can you start basic math series for trigonometry? Yes, I will. As a matter of fact, like I said, I'm arranging some stuff, and all of you will get to know about it. I think by God's willing, either tomorrow or the day after tomorrow, I'm going to kick off full works for those in basic classes as well too. All right, I'm going to kick off full work on that. 500 divided by 1,000. Okay, Ebere, please, sir. That 500 over 1,000 that you got 0.5. I was thinking that it is 0.2. Let's check. This 0 we cancel, 0 we cancel. 5 divided by 10 is 0.5. So it is correct. It's 0.5. All right. Why do I don't encourage you to use calculator for stuff like this? You can use calculator to find out. And once again, in the GMAETS 41's basic class channel, I deal with this concept under division a lot. So you can learn this concept from there. Question number 2, please. Let's move on straight on to question number 2. Now, question number 2 reads, or should I copy it on the board? I think it seems to be kind of faster. So as I just copy, you have it, we read it, and then go straight on. So question number 2, the quantity of heat required to raise the temperature. I'm going to abbreviate certain things. The temperature of 500 grams of iron by 2 degrees centigrade. Given that the specific heat capacity is 500 joule per kilogram degree Celsius is, so that's the question, the quantity of heat required to raise the temperature of 500 grams of iron by 2 degrees centigrade. Given that the specific heat capacity is 500 joule per kilogram degree centigrade is, we don't know. So we are going to solve, and then we have the options. I can dictate the option, that's no problem, right? Option A is 500 kilojoule. Option B is 0.5 kilojoule. Option C is 2 joules. Option D is 250. I don't know, is it? I'm saying 250K, group 2. Could this be 250 kilojoule? I'm going to assume that, okay? Option D, 250 kilojoule. But I'm not interested in all these options. The main thing is for you to know how to solve it. If you solve it correctly, there is no way you wouldn't get a correct option, a correct answer rather in the option, except if the options themselves are wrong. Okay, so from the question here, you see we are asked the quantity of heat required is what we are looking for. So we don't know the quantity of heat H. Let me now tell you what you are meant to do if you are seated in the exam hall, because if you are, let's say you are taking JAM where everything is CBT, you don't need to declare your data. It's not necessary. Let me close up this part a bit. You don't need to declare your data. Even in WAEC, in objective part, you don't need to show your workings. You don't need to say, okay, H is this is that. It's not necessary. If your brain can interpret that, you can go straight to the formula and then work on that. The quantity of heat required to raise the temperature of 500 grams. So we know the mass to be 500 grams. You know you have to convert this to kilogram of iron by 2 degrees centigrade. By, was it yesterday under thermal energy? I told you once you hear that something has been increased by, decreased by, reduced by, whatever by, They have given you the change in value. It is different from somebody telling you increase to means that the value they're going to give to you is the new value. But when I tell you, okay, to raise the temperature of 500 grams of iron by, they've given us delta theta, the change in temperature. So we're given a specific heat capacity. We are calculating heat. So our H is simply equal to, the formula is NC delta theta. NC delta theta. If you have that formula at heart, do you really need to write it in your solving sheet before you substitute? It's a waste of time. You only do that in the case of theory. Like in white theoretical part, you can show, you have to show your working. You declare your data first, H equal to question mark, you don't know. M equal to 500, then you show the conversion, 500 over 1000, which is 0.5 kilogram. And then delta theta, change in temperature, equal to 2 degrees centigrade. Then specific heat capacity, small c, equal to 500. You write the unit, you declare it, then you bring out the formula. As a recall, if it is in theory, H is equal to NC delta theta before you can now start substituting. I've been doing that a lot, and I'm trying to tell you that in the case of objective questions, you don't need that. Therefore, for this question, let us hit it directly in what you are meant to do in the case of CBT. I have the formula at heart already. My brain has interpreted what these guys are, and so I can just start solving directly. NC delta theta, our M is 500. With the network of my brain, 500 over 1000 is 0.5 kilogram. Good enough to have it here, so I guess it is clearer, times specific heat capacity, which was given to be 500, and then times temperature change, which was given to be 2. So that our H will now be equal to 0.5 times 500 is half of 500, which is 250. 250 times 2 is 500. You can still decide to solve this as 500 times 2, 1000. 1000 times 0.5 will give you 500. So this 500 joule, the unit is going to be in joule because there is nothing that is in kilojoule here. So the unit is going to be in what? In SI unit of energy, which is joule. Let us go to the options and see what we've got and see necessary conversions that we have to do. Now I have option A to be 500 kilojoule. Very dangerous option, isn't it? That is tricky because you solved and you got 500. If you're not good with units, you land yourself into trouble with that option. Please, since everything given here, right, there is nothing about kilojoule there, no kilojoule value. Like this specific heat capacity was not given in kilojoule, it was given in joule. Therefore, the value of this, the unit of this quantity of heat is going to be in joule. So that 500 kilojoule option A is wrong. It's not the same as this. Kilojoule value of this is to divide this 500 joule by 1000, which of course from what I'm saying goes with option B, because option B is 0.5 kilojoule. So this is 500 joule or 0.5 kilojoule. How do you get this 0.5 kilojoule? To convert from joule to kilo, divide that joule value by 1000. If you divide 500 by 1000, you get kilo value of that joule. So the correct option here is option B, right? That's the correct answer. We are done with the second question, number 2. Yeah, Chiagozie Andrew, that's good. That's correct. You got the answer. That's 0.5 kilojoule. I hope the class is still in progress. That has not cut off. Okay, that's good. And all part is showing. That's great, Shama. I am glad that you now understood this, right? I'm glad that you understood it. Let us move on, please, to our next question. There is no time. We have 10 questions to look at. Please remember to share this link to your friends, whether they are taking YJAB or not. If you are in SS1, SS2 here, share this link also to your friends. They need it, right? They need it. They need it, either now or later, as the case might be. If you're in advanced level, 100 level, 200 level, in one way or the other, you need this. In fact, even 300 level. Perhaps I can quickly talk about something regarding me, myself, right? In my 300 level in chemical engineering, there is this course I did in second semester. The course is titled Heat and Mass Transfer. Heat and Mass Transfer, right? Heat and mass transfer. Perhaps I can show you the textbook because I still remember in those days. So I'm not joking. Whenever this is a course, this is a textbook to the course. You can see heat and mass transfer. Those in chemical engineering will know this textbook, ARRK Rajput. This is all about heat transfer. And the foundation of that heat transfer is what you are learning now at this level. Are you following, right? This topic you are seeing is SS1 topic. SS1. But you see, it is the foundation of something that is done in advanced level as high as 300-400 level. Even 500 level, I still treated something related to this in transport phenomena, chemical engineering. FST, food science and technology, you are still going to do a course later. In fact, this cannot be overemphasized. So whenever you see something because it is labeled JAMB or SS1, okay, basic level, it doesn't mean you take it for granted. You might need that in one day. Let me return this to my library. So in as much as this class is taught, O-level work, wide JAMB, those in advanced level, don't play with it. Okay, you want to work hard. You need them as well. You need this stuff as well too. All right, let us move on. Besides, in lots of industries, they deal with heat transfer. And this is the concept, the basic concept, the startup point. Question number 3. It is not calculation. Question 3, Q3. So since it is not calculation, I'm going to dictate it. Heat energy is measured in. Heat energy is measured in. Heat energy is measured in. I won't give you the answer. I would dictate the options, then please, someone should drop the correct option there. Heat energy is measured in option A, Kelvin. Option B, watts. Option C, kilograms. Option D, joules. Joules. I was telling my JAMB student that joules is actually, the correct pronunciation is joules, right? Don't mind that. Joule. So what is the unit, the correct unit of heat energy? It is measured in watt. So I am waiting to receive your answer here. Someone has dropped his own answer that heat energy is measured in kilogram. I don't think I agree with that. While I'm waiting for other options, let's move on to question number 4. But I'll leave a space for what the correct answer is. Whomever gets the correct answer is going to win. I'm going to gift that person 500 airtime, 500 units of airtime. 500 units of airtime. The units, right? Is it let me see that the question is heat energy is measured in. Heat energy is measured in. Whomever gets it, like I said, is going to be gifted 500 units worth of airtime. Option A is Kelvin, B watts, C kilograms, D is joules. So let us move on to question number 4 as I wait for the correct option. Amarachi and Nita Godwin, option, you say joules, that's good. Daniel, you say joule, that's good. Satya Abdullahi, you also mentioned joule. So there are 3 entries that appeared here that are correct, and now that the correct answer has been mentioned, I will pick, okay, let me just give the last consideration because someone also still just dropped. Spike enthusiast. So that is all. I have 4 people here. The 4 people are going to be gifted each 500 units worth of airtime. How do you get it? Send a message to this number on WhatsApp. Send a message to this number on WhatsApp, right? You must tell me your name. You must tell me your name on YouTube. It's because any other person could send to want to claim it. Right? Any other person could send to want to claim it. And I have gotten down the people who are going to be gifted that. The first person here who dropped the first entry is Abdullahi Fatia. The person said it's Jos, which is correct. Then Ebere, you said, Ebere, yours just came in. Yours just came in, so I don't think you're among. But thank you for bringing up your answer. The next person I saw is Daniel, right? And good. Number 2. Then Amarachi, Anita Godwin, number 3. Spike Enthusiasts, number 4. So 4 of you. The others, you are dropping, and that's correct, no problem. Okay, Eberi, you're claiming you are the second person that dropped. I really didn't see that, but no problem. I'll add you up, making it number 5. So take notes. Each of you will be gifted that. Send your phone number, your contact number that you wish to be recharged to my contact on WhatsApp. At the end of the class, you will receive your airtime. Although the question is 1 plus 1 anyway, the units or heat energy is measured in joules. The correct option is D. Option D, which is joules. Option D, joules. All right. We are moving on, please. Question number 4. A change of temperature of 20 degrees centigrade. A change, this does not require any calculation math, so I won't write it on the board. A change of temperature of 20 degrees centigrade is equivalent to a change in thermodynamic temperature of a change of temperature of 20 degrees centigrade is equivalent to a change in thermodynamic temperature of option A, 293 Kelvin, option B, 20 Kelvin, option C, 80 Kelvin, option D, 120 Kelvin. Once again, a change of temperature of 20 degrees centigrade is equivalent to a change in thermodynamic temperature of option A, 298 Kelvin, option B, 20 Kelvin, option C, 80 Kelvin, and then option D, 120 Kelvin. Solving this is simple. It's just for you to add 273 to the given 20 degrees centigrade. Thermodynamic temperature in SI unit is actually measured in Kelvin. And if I give you a value in degrees centigrade to convert to Kelvin, you add 273 to that degree centigrade or Celsius value. So we are giving theta to be equal to 20 in degrees centigrade. So theta is now equal to 20 plus 273 in Kelvin. If you add up this, you get 293 Kelvin. And therefore, the correct option is option A. We are moving on to question number 5. Remember, we'll have 10 questions to deal with in this live stream. And by 8, we are moving on to chemistry. So I'm going to be very fast. It's 7:10 already here in Nigeria. So for our friends from other parts, okay, let me allow you to copy that. This is 0.95 times 10 to the power of 3 joule kilogram. If you've not copied this, make sure you screenshot so that we move on to question number 5, because by 8 o'clock, we've got chemistry to deal with. In chemistry, we are going to look at problems, questions on electrolysis. That was sent by, I think, group 3? Now, that should be group 8 or so. I can't remember. So we are moving on. You can become a member of GMAS 41's channel. All right, join our WhatsApp group. Become a channel member, join our WhatsApp group. And all of you that are members of the GMAS 41's channel, that are members of our learning community, either you join at platinum level or at diamond level, please, I am announcing this now. If you are a member of our channel, by joining the channel, you can join either at platinum level or at diamond level. If you are so grateful about what GMAS 41 is doing, you can join at diamond level. What is there? You're supporting your favorite creator, so I can continue to do my best. It's not easy. A lot of resources, energy, right, goes into these stuffs. I've been talking about how I burn petrol regularly, because this part where I am, for I think more than 2 months or so, I've not seen light from our electricity production company. Oh, no, but that's it. We don't even remember that we have any such as a company anymore. So petrol is being used. I can imagine how much we buy a liter of petrol right now in this country, in Nigeria. So please, your support is needed, and I will appreciate it. So if you are a channel member at platinum level or diamond level, because that allows you to support this channel every month, all right, monthly. Platinum level is 2K, 2,000 monthly. Diamond level is 4K, 4,000 monthly, whichever is convenient for you out of the two. So if you join this channel at that level, please send a message to my contact, my number on WhatsApp, so you can join our learning community, because you are a full member of the GMAETS 41's channel. Let us move on to question number 5. Question 5 is calculation of question 5. And it's long. It's long. So I won't have the time to write on the board fully. Or should I write on the board? This is serious. Let me dictate it. Pay keen attention, and you can be fast in writing. In an experiment to find a specific latent heat of steam, the mass of calorimeter was 50 gram. Permit me to use MC equal to 50 gram, which is 0.05 kilogram if you divide by 1000. This MC, I'm using it to represent mass of calorimeter. Total mass of calorimeter and water was 300 gram. Total mass of calorimeter and water is 300 gram. So permit me to use MC plus M water. Mass of calorimeter plus mass of water is 300 gram. Which of course, from here you can get the value in kilogram. This is going to be 0.3 kilogram. This is the total mass of calorimeter and water. And from here, in fact, anyway, no problem. Let's read out the question first before I do any analysis that is not from the question directly. Okay, we'll move on. Total mass of calorimeter and water was 300 gram. I've done the conversion. The initial temperature of water in the calorimeter before steam was passed. The initial temperature of water in the calorimeter before steam was passed was 20 degrees. So I'm going to write theta W1, initial temperature of water before steam was passed, 20 degrees centigrade. The temperature increased. Okay, before then, let me still read. The initial temperature of the water in the calorimeter before steam was passed was 20 degrees centigrade. The temperature increased to 65 degrees centigrade. So we can say that final temperature of water in the calorimeter, 65 degrees centigrade. The temperature increased to 65 degrees centigrade after steam of total mass. After steam of total mass, 16 gram was passed. After steam of total mass, 16 gram was passed. So mass of steam is 16 gram. That 16 gram can be converted, divide by 1000, you get 0.016 kilogram. The question is still going. See why I ran from writing it on the board. The temperature increased to 65 degrees centigrade after steam of total mass, 16 gram was passed. Assuming that the steam was 100 degrees centigrade, assuming that the steam was 100 degrees centigrade, that is the initial temperature of the steam. Initial temperature of the steam, let me use theta S1, initial temperature of steam, 100 degrees centigrade. Estimate the value of the latent heat of vaporization. Estimate the value of the latent heat of vaporization of steam. Estimate the value of the latent heat of vaporization of steam. We don't know. Estimate the value of latent heat of vaporization of steam. Then in brackets, specific heat capacity of calorimeter equals 400 joule per kilogram per Kelvin. Specific heat capacity of calorimeter, let me use C, subscript C. Specific heat capacity of calorimeter equal to 400 joule per kilogram per Kelvin. And then specific heat capacity of water specific heat capacity of water, let me use CW. CW equal to 4,200 joule per kilogram per Kelvin. I hope this does not cut from the space there. So, okay, that's good. Everything is showing. Everything is showing. We're going to speed up. Let us see what we have there. So, you were asked to estimate L. We don't know L. We don't know L. So, what should you understand about this question as a whole, right? What should you know about this question as a whole? This is simple as, see, you have a calorimeter. You have a calorimeter, let's just say a container. The container contains water. The container contains what? Water. Then you now pass steam into that container. It's just like you having a bucket of cold water. A bucket of cold water, and you now boil the water. After boiling the water, you decide to pour the water into that container that is containing the cold water. You know, there is going to be a concept of heat transfer. Heat to be lost by the steam and heat to be gained by the calorimeter and the water that is contained in the calorimeter. So the question here is about heat lost equal to heat gained. Heat is lost by the calorimeter, by the steam, and then heat is gained by the calorimeter and the water in it. Questions like this, what you do is simply to solve total heat. That, okay, the heat that is lost by steam. Heat lost by steam will be equal to heat gained by calorimeter, by water and calorimeter, by water plus heat gained by calorimeter. Permit me to abbreviate calorimeter as cal. That is just a simple interpretation, right? A calorimeter contains water. The initial temperature of that water is 20 degrees centigrade. You pass steam into that water. Definitely when you pass steam into the water, the temperature of the water will rise, will increase. That is what happens when you want to take hot bath, right? You want to take hot bath. You boil your water, you pour into cold water, and then the cold water temperature is elevated to the temperature that your body requires. Then you bathe. And you know, if you have water in the container and that water is hot, the container also will gain heat. That is why we say that heat lost by the steam is equal to heat gained by water plus heat gained by what? Calorimeter. And this is just the analysis. So what do? We are asked to calculate the latent heat of vaporization. The latent heat of what? Vaporization of steam. Now look at this. Let us look at the condition of steam. Initially, the steam was at 100. You know, steam at 100. Now, observe what happened. When you pass the steam to water in that calorimeter, the temperature of the water in the calorimeter increased to 65. You see this temperature? This temperature is the temperature of mixture. It's the temperature of what? Mixture. Just like you have cold water and you're now pouring hot water into it. As you pour the hot water, at a point, both the cold water and the hot water that was poured will now reach the same temperature. We call it final temperature. We call it steady state temperature. We call it the temperature of the mixture. I don't know if I'm communicating. And the temperature of the mixture is the same for both of them, which is the final temperature of the water and calorimeter will be the same as the final temperature of the steam, and of course, the final temperature of the steam. So this is what you want to take note of. The steam reduced its temperature from 100 to what? 65. But hey, that steam is going to become liquid water. Yeah, it's going to turn to water, liquid. Steam is gas, you know. So when you pour that steam, which is gas at 100 degrees centigrade, if you pour it into that water in the calorimeter, the steam will start losing heat to the water in the calorimeter. Then the steam first, take note, this is where it becomes critical in interpreting this question. That steam, which is in gaseous form, will first of all change to water. You know, if you are boiling water, water boils as a liquid at 100 degrees centigrade. And then from that liquid water from at 100 degrees centigrade, the molecules of the liquid will start evaporating, will start vaporizing rather. When it starts vaporizing, there is no temperature change. Remember latent heat. When water at 100 starts vaporizing, you have that water as liquid at 100 degrees centigrade. As it is changing to vapor, to steam, it is still 100 degrees centigrade. So if the steam is now changing, when you pass it to the water, the steam at 100 loses heat. It will change to liquid water at 100. Change your state, latent heat. There will be no temperature change. Then the steam now that has changed to water at 100 will start losing heat again. We'll be losing heat to the water in the calorimeter. The water at 100 from the steam at 100, the water at 100 will start losing heat again from 100. The temperature will start reducing. In that case, there is no change of state because it's just water at 100 degrees centigrade losing heat to water at 20 degrees centigrade. What is going to happen is water at that 100 degrees centigrade now will reduce the temperature to 65, which is the temperature of mixture. This interpretation, by the time I'm done with this lesson, a copy of this video will be made available, so you can still come back to listen to this particular interpretation here, because that means that this part of the formula is going to be heat lost by steam at 100 degrees centigrade plus heat. This is going to get to this guy at that 100 degrees centigrade to heat at 65 degrees centigrade, because the final temperature will be 65. Once this guy loses heat from 100 degrees centigrade, it will turn to water at 100 degrees centigrade. So we have heat lost by steam at 100 degrees centigrade to water at that same 100 degrees centigrade. There is no temperature change. This one is going to give us NL, mass of steam times the latent heat of steam. Since there is no temperature change, what changed there is just the state of matter. Water in steam form changed to water in liquid form, still maintaining that temperature 100 degrees centigrade. Then here will now be heat lost by water at 100 degrees centigrade to water at 65 degrees centigrade. Because once the steam enters the water, like I said, it enters the water, it loses the steam form, turn to water at 100, and then from that 100 degrees centigrade, it will be losing heat to the water that was at 20 degrees centigrade inside that calorimeter. So from 100, this guy is losing from 100 down to what? The final steady state temperature of mixture, which is 65. And that is what I have indicated here. In this case, you no longer use ml. There is no change of state here. This is water at 100 to water at 65 degrees centigrade. So there's going to be a change in temperature, MC delta T, delta theta. This will now be equal to these two heats are the makeup of this heat lost by steam. The right-hand side will now be heat gained by water. So this is going to be heat gained, and now gained by water. Let me abbreviate water with the chemical formula. At 20 degrees to water at 65 degrees. Then plus heat gained by calorimeter cal. Writing this heat in full. I'm going to abbreviate, there is no much space. So heat gained by calorimeter cal at, remember the calorimeter, since it is containing water, the initial temperature of that calorimeter will be the initial temperature of water, which is 20 degrees centigrade, and then to 65 degrees centigrade. To 65, because the temperature of the calorimeter will be increasing as the temperature of the water inside the calorimeter is increasing. So this is just the analysis of the stuff, and I think we are good to go in solving this question. I'm trying to be a bit fast now so I can round off before the time of the chemistry. The chemistry is just at 8 o'clock. But it is necessary that I take my time to analyze this. Is there any student that captures this explanation? There is no calculation under measurement of heat energy in the concept of heat capacity, specific heat, latent heat that you cannot solve. With this now we can substitute. Heat lost by steam at 100 to water at 100 is simply ml. It's simply what? ml, mass of steam. Mass of steam times latent heat of vaporization of steam. And mass of steam, I guess it was given to us 0.016. And then this is plus, coming to this, heat lost by water at 100 to water at 65 is going to be MC delta T, which is mass of water, specific heat capacity of water, then times temperature change, which is going to be theta 2 of water minus theta 1 of water, or theta water 1, then water 2. Good. Then on the other side of the equation, heat gained by water at 20 that increase the temperature to 65 is still going to be mass of water times specific heat capacity of water, open bracket, theta 2 of water, and now theta water 2 minus theta water 1, change in temperature, plus that of calorimeter, which is plus mass of calorimeter. Were we given a mass of calorimeter, we can find it is mass of calorimeter, but we were not given mass of water. That was what I had wanted to do here, but I just said, let's finish up the question, right? I don't know where this group 2, group 2, you guys are funny. I mean, you guys are not funny anyway. Going far to draw a question from it, but it's okay, it's good. These are the type of questions they ask in WIAC theory cases. Now we are moving on. Where are we? Mass of water is going to be 0.3 minus mass of calorimeter 0.05. That will give us mass of water, so we don't have problem there. Mass of calorimeter times specific heat capacity of calorimeter, then times temperature change, which I said is still the same thing. It's going to be theta of calorimeter 2 minus theta of calorimeter 1, which is the same as that of water. So having expanded this concept, having expounded it, giving you the clear interpretation of this question, I think we can now substitute our values and solve for MS. I mean for L rather, latent heat. So this is going to be mass of steam is what? I'm fixing up the values, 0.16. I hope this shows in the screen. Let me see. Let me find out 0.016. So it showed, it didn't cut off. 0.016 times latent heat, we don't know. And then plus mass of water. Mass of water is going to, remember, calorimeter and water is equal to 0.3. Mass of calorimeter alone is 0.05. So mass of water is going to be 0.3 minus 0.05. I don't have time, so I'm going to use calculator. 0.3 minus 0.05, and this gave us 0.25. That is mass of water. So note, but mass of water is equal to mass, total mass. Let me call this the total mass. I'm using N. Minus mass of calorimeter, which is 0.3 minus 0.05. If you do that, like I found out, is 0.25, right? 0.25 kilogram. So I'm trying to be a bit fast. So this is 0.25 times the specific heat capacity of water, which is 4,200, then times temperature change, that of water from 100 to 65. From 100 to 65, it's going to be, remember, heat is being lost. And we are talking about heat being lost from 100 to 65. In the case of the steam, the heat is reducing. So the temperature is coming from higher temperature to lower temperature. I know this concept of heat. In terms of the temperature, it is final minus initial. So this is going to be 65 minus 100. 65 minus 100. Not 100 minus 65. Take note. That's going to be equal to, go to the other side of the equation, do the same thing. You're doing the same thing, mass of water. Mass of water is 0.25. Okay, then times specific heat capacity of water, 4,200, times the temperature change of water. In this case, the water gained heat in the calorimeter, so it's from 20 to 65. The temperature change will be final temperature 65 minus initial temperature 20, plus the part of the calorimeter, right? Mass of the calorimeter is given to be 0.0, let me write it here, 0.05. That's the mass of calorimeter. Then specific heat capacity of calorimeter is given to be 400, and then times temperature change. The temperature change again is from 20 to 65, so 65 minus 20. I've done the substitution, we can now solve. So this means that 0.016 times the latent heat of vaporization of steam will now be plus, let me reach out to my calculator. We've got to press quickly. I think this is not going to be plus anymore. It's going to change to minus. I'll tell you the reason. The reason is because 65 minus 100 will give you minus 35. minus 35. That minus, if you are multiplying out this part, we change this plus to minus. So we're going to get minus 35 times 0.25 times 4,200. So what do we get here? This is minus 36750. And then that's going to be equal to, you come to this part, you do same, right? 65 minus 20, 65 minus 20. All right. And then this gives us 45. Multiply the 45 by 0.25 times 4,200. And then you get this to be 47,250. Then you are adding it to you are adding it to this part. 65 minus 20 is 45 still. 65 minus 20, 45. We are multiplying it by 400. We are multiplying by 0.05. And so this gives us 900 here. Automatically, the latent heat of vaporization of steam is this plus this divided by this. 47,250 plus 900. You know, this 36,750 we cross. It becomes plus 36,750. We are dividing all of this by the coefficient of the latent heat, which is 0.016. So 900 plus 47,250, and then plus 36,750. We are dividing this by 0.016, and the value is 5306250 in joule. That is 5,306,250. We can also rewrite this as 5.3 because you can move your point from here 1, 2, 3, 4, 5, and 6. 5.31 approximately times 10 to the power of 6 joule. So this is what the value would be. This is what the value would be. And that's the analysis. That is the analysis. The options given here does not fit. We have 2.67, 2.88, 2.86 times 10 to the power of 6 and the rest. Option D was not written. Group 2. You did not write option D. I don't know why. Are you following? But the option A, B, C you provided, they are not in line with what we got here. Are you following? They are not in line with what we got here. This is what we obtained. 5.631 times 10 to the power of 6 joule. That's in millions. We are done with this. Question number 6 is similar to that. And so I am going to jump that. We don't have time to spend all of those times, but I will dictate the question. I'll dictate it. So when the copy of this video, this lesson is made available, you can come back, copy the question, and then see how you attempt it based on the explanation I gave you. So we have this question. A copper calorimeter weighing 40 grams contains 200 grams of water at 35 degrees centigrade. 20 grams of dry ice is added to the water. 20 grams of dry ice is added to the water, and this reduces the temperature to 25 degrees centigrade. And this reduces the temperature to 25 degrees centigrade after all the ice has melted. What value of specific latent heat of fusion of ice is given by this experiment? What value of the specific latent heat of fusion of ice is given by this experiment? In bracket, specific heat capacity of water equal to 4,200. 4,200, you have the unit already. Specific heat capacity of copper is 400. You have the unit already, 400. So you fix up the unit. So you can attempt this, but take note, this is not in terms of steam anymore. This one is in terms of ice melting. But the interpretation follows the reverse of what I said. If you have ice, dried ice, that ice will melt from whatever temperature it was, as mentioned in the question, right? It's going to melt. Say water at 35, 20 grams of dry ice is added to the water, and this reduces the temperature to 25 degrees centigrade, you know, after all the ice has melted. So here you have ice. Ice will be at 0. You know, ice is solid. When it is melting to liquid, it will be ice at 0 to water at 0 degrees centigrade. Ice at 0 degrees centigrade to water at 0 degrees centigrade. In that case, there is a change of states from solid ice to solid water to liquid. So use ml there. Use what? ml. Then for the ice to reduce the temperature again to that 20-something degrees they said. Are you following, right? For the ice to reduce the temperature, I think the question said to 25 degrees centigrade. It means that the ice itself, when it was melted, it melted from ice at 0 to water at 0, then from water at 0 to water at 25 degrees centigrade. Why the other water you added that ice to? The initial temperature of the water is from 35, so it will reduce to that 25. That 25 is the temperature of mixture. So use that analysis. I am going to release a special pre-recorded video on this particular question. But like I said, this one, if you understand what I did here, it will guide you to deal with this particular question. We won't have that time to analyze the question right now because of time constraint. Like I said, we are preparing for chemistry. So I've got to round off this. Chemistry is by 8 o'clock. All right. So we are moving on to the next question. We are moving on to the next question, number 7. Number 7. Finish up with what is on the board so that I can wipe it. Let me adjust this camera. It's not showing. Let me adjust this camera. Gozie Andrew, you posted 47,798. That is not the answer. But thank you for attempting. Are you following, right? It's not easy. Thank you for attempting. But I just want to hope you did not just drop any value you want. Thank you for attempting. So you can see the board while I wipe it off. You can screenshot. So that I can wipe it off. Let's move on. Time is not our friend right now. Question number 7. I've told you number 6. I'm going to skip it. I dictated it for you so you can solve it. Like I said, I think let's see what happens tomorrow. I'll release a video lesson on it. Remember, like I said, I have lots of pre-recorded video lesson on different topics in different courses: chemistry, physics, math, and other engineering courses. Are you following, right? You can actually slide through to my main channel. How do you get to that place? Just click on any of my video. Then the GMAETS 41's logo or icon, blue, you have G41 channel. Click on it. It will take you straight to my channel, to GMAETS 41's channel, where you will see only GMAETS 41 stuff. Go to the playlist. Go to the playlist and then you see courses. Like I've always mentioned, academic wonders are there. Let's move on to question number 7. I'll skip number 6. I've told you my reason, but I've dictated it. It's not as if I can't attempt that question. It's not as if I can't solve it. It's still 1 plus 1. Are you following, right? In fact, that question is even simpler than this one of STEAM that has been analyzed. It's simpler than this one of STEAM analyzed. But because of the time it's going to take us, let us move on to question number 7. Question number 7 is not calculation. Q7. I'll dictate it and then answer the question straight. What is latent heat? What is latent heat? During the background explanation of this topic, I defined it. A, the heat per unit mass required for a phase change to occur. The heat per unit mass required for a phase change to occur. And of course, that makes sense to me, that definition, because I remember I'll talk about this to be H divided by M. So option A said it is the heat per unit mass required for a phase change to occur. Option B, the temperature change resulting from the temperature change resulting from a change in energy. That is wrong. When you're talking about latent heat, there is no temperature change. Option C, the internal energy of a substance. The internal temperature rather of a substance. Option C, internal temperature of a substance. That is wrong. Then option D, the resistance to the change in temperature. The resistance to the change in temperature. Does it actually define resistance to change in temperature? We are asked what is latent heat. So that is not the definition. The correct definition to latent heat here is option A, the heat per unit mass required to cause a phase change, required to cause a change in state. So the correct option is A. I've even written the formula here for you to see. Now we move on to question number 8. It is not calculation also. Thank God the rest are not calculation. So we can round off, even if it is 5 minutes, we rest before 8 o'clock as I kick off chemistry. There is no time. Besides, in your various schools, don't you take class, you know? Say you start your classes by 9, maybe the secondary school, and then you run the class till 12 before your long break and other things. Those in university, you know how long you stay sometimes. All right, this is learning at your own pace. So you can always join the class again if you have something to do. We are moving on, question number 8. Which of the following processes could be described using the latent heat of fusion? Question 8. Which of the following processes can be described using the latent heat of fusion? A. Melting ice to form liquid water. Melting ice to form liquid water. Option B. Freezing water to form ice. Freezing water to form ice. Option C. Both of these are correct. Option C. Both of these are correct. Option D. Neither of these are correct. Option D. Neither of these are correct. This question is tough, right? You see, whenever you hear latent heat of fusion, the first thing that comes to mind is where solid is changing to liquid. I've talked about that. I explained that during the background, the summary work to this topic. So one could think that, okay, option A, melting ice to form liquid water, and that's what makes sense to me in terms of latent heat of fusion. However, the question is, what if the water is freezing to ice? Which term do we use for it? Is it latent heat of condensation? I don't think I've heard of latent heat of condensation before, even though that process of water changing to ice, is called condensation. But I've not heard where that term latent is used with condensation. Okay? I've not. So since they change from, they change from ice to liquid. The reverse of it is liquid to ice without a change in temperature. Both processes can be described using the latent heat of fusion. Both processes can be defined using what? The latent heat of fusion. Do you get that right? Because the question did not specify which of the following processes could be described using the latent heat of fusion of ice. If it is say fusion of ice, then okay. So I think for me, both of these are correct. If I'm seated in the exam hall, I'll go for C. You can use it to describe a situation where ice as solid changes to liquid, which is the major thing we encounter. But if the process is being reversed, where water is freezing, liquid is freezing to solid, maybe liquid water freezing to ice water, we can still describe that as a latent heat of fusion, because it's just an opposite process. So option C is what I found to be correct to me. Might be different from you. You can throw up your own suggestion and then we analyze it critically. But let's move on to the next question. Number 9. The heat energy required. Question number 9. The heat energy required to change 1 kilogram of a substance. The heat energy required to change 1 kilogram of a substance from a liquid to a gaseous state at the same temperature, that is no temperature change, is called, I repeat that again. The heat energy required to change 1 kilogram of a substance from a liquid to a gaseous state at the same temperature is called, I'm not going to answer that question. I only dictate the option. In the summary work, I'd already defined these thoughts, and I took my time to emphasize on them, much rather. So option A, specific heat capacity. B, specific latent heat of vaporization. C, sensible heat. D, specific latent heat of fusion. Now I'm going to help you. I will streamline the options so you now make use of 50-50. Option A is specific heat capacity. Option B is specific latent heat of vaporization. Option C is sensible heat. That is not the answer. So forget about the sensible heat. Option D is specific latent heat of fusion. That is not the answer. So forget about it. We are talking about fusion. Like I said, generally it is used for the hidden heat, the latent heat, the heat that is hidden when solid is changing toward liquid. Your answer is between option A and B. But I'm going to tell you something. One of the options between A and B, specific heat of this, specific latent heat of, one of them is used in the case of solid. The other is used in the case of liquid. So tell me what the correct answer is in question 9. Like I said, the question number 9, the answer is between A and B. So tell me what the correct answer is as we move on to the last question, number 10. Let me give it space a little. So question 10. Remember in that question 9, why the answer is the ones of specific. Are you getting me? But I've told you it's not D. D is specific latent heat of fusion. That is off. Yeah, although that one is solid to liquid. But if you look at your question, you know what they're talking about. Question number 9. The heat energy required to change 1 kilogram of a substance from a liquid to a gaseous state at the same temperature is known as what? All right, so somebody should drop the answer. Question number 10. The temperature of pure melting ice. The temperature of pure melting ice is what? What is the temperature of pure melting ice? Option A, 373 Kelvin. That is not the answer. 373. Option B, 273 Kelvin. I will not tell you whether that is the answer or not yet. Is a suspect. There's a reason why I don't want to tell you, because of another option we'll encounter. Option C, 100 Kelvin. That is not the answer. Option D, 0 Kelvin. Someone might be confused with that particular option. In fact, option C can also confuse 100 Kelvin. So you want to watch out this. Having heard the whole options, the correct answer is option B, which is 273 Kelvin. Now look at it. If pure ice is melting, it occurs at 0 degrees centigrade. And if I give you pure ice melts at 0 degrees centigrade. I think in question number 5, I guess we did something like that. Pure ice melts at 0 degrees centigrade, or this 0 degrees centigrade converts to 273, because you know to change from degree centigrade to Kelvin, you add 273. So 273 Kelvin. So do you see why the correct option is B, 273 Kelvin? And do you now see why the answer is not D? Because D said 0 Kelvin. 0 in Kelvin is equivalent to minus 273 degrees centigrade. If you are quoting melting point of ice as 0, please, the unit is degree Celsius or centigrade, not Kelvin. So the correct answer here, like I said, is option B, right? That's the correct answer. Now, back to that question 9. Have you dropped your answer? Have you dropped your answer? Back to that question 9. All right, Elijah, you dropped the option B, specific latent heat of evaporation. Okay, specific latent heat of vaporization. All right, Buzoman, you say B, correct. Ebere, you say B, correct. All right, question 9 is B. So that is the correct thing. The correct answer to that question 9 is specific latent heat of vaporization. That is the quantity of heat required to change 1 kilogram mass of a substance from its liquid form to its gaseous form at the same temperature without a change in temperature. So guys, this is how we have come to the end of our class on physics today, and I hope you learned something wonderful from this concept of measurement of heat energy. If you do love this video, what holds you from giving it a like? Give it a like, then come back later when a copy of this video is made available, just shortly after this class. Then type a comment of appreciation, right? Okay? Share this video to your friends, to others. Share it. Let it go viral. Many people out there need this. They need this. There are many students that have had this class in school. Unfortunately or sadly, they did not understand it. Yes, that's the truth, right? So share it to them so they can learn from this. And finally, you can support GMAETS 41's channel. You can support me, right? If you see me as a creator that you appreciate based on what I am delivering, just around the comment section, right, the chat box of this particular lesson, you have the currency icon. If you click on that currency icon, you will see super stickers, you will see super chat, you will see membership. You can tap on any one of them and then you send GMAETS 41, whatever that is convenient for you. All right, support this channel, I appreciate. To become a channel member, you can click on that unlock members only perks, and then you join this channel. You can join at platinum level or you can join at diamond level. That gives you room to support this channel every month. Platinum level is at 2K, 2,000 per month. Diamond level is at 4,000 per month. But that of super stickers and super chat only gives you room to support GMAETS 41 just once. It's one-time support. If you go for channel membership, if you go for channel membership, I will greatly appreciate. Yes, to be honest, I'll greatly appreciate, because you see what is happening on this channel. You see, it's wonders, right? It's wonders. Not only one subject, you know, but the basic science subjects, STEM subjects, maths, chemistry, physics, English, you know, and of course, biology will soon come up with time, working towards that. So please support us, support GMAETS 41. And then once you become a channel member, please immediately send me a chat. Send me a chat on this contact on WhatsApp so that you'll be added to our WhatsApp group straight on. Right? We have a special WhatsApp group for you friends also. Then for others, you can also join our general or public WhatsApp group. I love you guys, and I want you to take your studies seriously as always, okay? I would be live again soon by 8 o'clock. We're supposed to kick off chemistry, but I think it's going to start by 8, let's say 8:30. All right, by 8:30, we're going to kick off chemistry with electrolysis work. See you later by 8:30 p.m.